Hello folks, this is Tom from anti-proton.com, and I'm doing a short little video here to explain, to answer a question I got. I got a question from, let's see, look at my iPad here, Cron009. Cron was interested in gravity, near misses, that sort of thing. Apparently there's a lot of people on YouTube and around the world who are kind of interested in what would happen if a near miss occurred, asteroids and comets and that sort of thing flying by the Earth, and how dangerous that is. Of course, it's always dependent on the size of the asteroid and its mass as well. I'll warn you, during this video I might be attacked by my cat. My cat keeps coming to see me. The cat is very interested in mathematics. It's actually one of his skills. And so, of course, naturally, he's attracted to this. So you might see him run by. My wife will run by and grab at him and tear him away. I drew a giant G for gravity and this little trajectory bending around it, which is totally pointless, but just for your benefit. I'm going to make this quick as I only get 10 minutes, which is sort of annoying. But, you know, that's the way it is on YouTube. Okay. First off, let's erase this big G here for a second. There. The cat got away. It's still coming. So we just got this new cat in. It's just like crazy. Alright. The way one determines the effect of one mass upon another mass, see, mass 1 and mass 2, is using Newton's good old-fashioned understanding and laws and whatever of gravity. They're pretty simple to understand. See, there's the cat. There's a stain the cat made. Isn't that great? We have to get all this cleaned up, of course, because the cat is, well, a cat. It's driving us nuts. Alright, to do this, the math, the formula is pretty simple. The force between any two masses is equal to the gravitational constant of the universe, which I'll tell you about in a second, multiplied by the sum of both the masses. In this case, you could have Earth, the sum of Earth in kilograms, and a comet that's going to pass by in kilograms. You add them together, and you divide them by the distance in meters. This is meters, believe it or not, even though it's an R, don't ask me why, squared. So you sum, 100 kilograms plus 200 kilograms divided by 50 meters. You get the point. It's pretty ridiculously simple math. And then this is multiplied by the gravitational constant of the universe, which last time I looked up on the internet is like, what is it, 6 point something times 10 to the negative whatever power, let's see, meters cubed, that's not meters cubed, mass cubed multiplied by, what is it, 1 over kilograms multiplied by seconds squared, I think. You look it up on Wikipedia if you like, but basically this unit becomes newtons, and it will spit out a formula of Newton's. Let me give you an idea. I'm not doing a math class here per se, as much as trying to explain it to you a little bit. You get the point. You're adding up the sum of the Earth and the asteroid that's coming in. You're pretty much dividing it by the distance squared. The bigger the distance between the two, the less effect it has. Makes sense, right? Here, let's look at a near-Earth miss. Here's Earth. There goes the cat running away. Just leave the cat. It'll be fine. See? There he is. He's hiding. He's a math cat. There's Earth. And it is approximately, give or take a few ounces here, 6 times 10 to the 24th kilograms. That is a hell of a lot of mass. That is a stupid amount of mass. Alright? It is a distance of, let's see, here's our comet. See? Unhappy comet. It is a distance of 1,000 kilometers, let's say. And this is for an instantaneous calculation. In reality, during the entire time of its approach, this number will increase and then decrease as it goes by. Let's say our comet's 1 times 10 to the 6 kilograms is 1,000,000 kilograms. And here's our little formula. Force equals gravitational constant of the universe. For this number, you put in this number. For this number, you put in this number. For this number, you put in this number. That's actually not too difficult, right? It's not actually that complicated. If you know a little bit about math, you can do it. If you want, I can do a video where I can actually sit down and just walk you through the entire calculation. That wasn't the point of this video today, but if you want that, I can provide the video where I do that. It's up to you. Okay? The result is equal to, and I just threw this through a calculator because I'm lazy, 400,365,000 newtons. I ran through a calculator, so I hope that's about right. I was being lazy this morning, but that sounds like a lot of newtons, about 4 million newtons. Let's examine that for just a second. This is a force felt at any given instant. Well, this particular given instant actually is this little comet's going by. Consider momentum for a moment. The Earth has a velocity of approximately, and I know I'm actually not giving you velocity, I'm giving you a speed because velocity has direction, and I'm not talking about the speed, or I'm not talking about the direction of the Earth, I'm just talking about the instantaneous speed it's going, not its velocity exactly, but we'll call it velocity, of about 29.8 kilometers every second. Oh my God. And remember, folks, momentum, which is a P, don't ask me why, physicists like to use weird letters, is always equal, in our case at least, to mass times velocity. So, oh my God, this number, 29.8 kilometers per second, 29.8 thousand meters per second, multiplied by 6 times 10 to the 24th kilograms. Oh my God, that's a humongous, ridiculous, ludicrous velocity the Earth is going. Compared to this little stupid thing. It's like a BB trying to stop an oil tanker. Let's look at that for a second. If a space shuttle is equal to about, shuttle is equal to, let's say, 2 million, give or take, kilograms of weight when it starts taking off. And we know that Newton is the force that required to move 1 kilogram to a velocity of 1 meter per second. So let's take this space shuttle here at 2 million kilograms, and we'll grab a hold of it right as it very first starts. In that very first tenth of a second, when it increases from a 0 velocity to, let's say, 1 meter per second, so this is like the first tenth of a second, right? Because it speeds up pretty quickly. And if we take that and divide it by the number of newtons that we found a little while ago, we'll come up with 196 space shuttle launches to equal that comet going by. I'm pretty sure 196 space shuttle launches, even at one time around the world, is not going to affect our velocity too much, because the Earth is just so big. To get down into the concept of what we're dealing with here, and let me take this and erase this for a second here with my hand. What we're dealing with really basically is a plastic material called the universe. I know it's kind of a little over the top for me to claim that I understand how the universe is shaped, and I can't say I do for sure. But this is generally a relatively held scientific belief. The Earth is, all massive objects like this one right here, you could think of them if you wanted to think of them, and we're going to call this, for any scientist out there, a two-dimensional conceptual manifold of a fourth-dimensional concept. But for you non-scientific folks, let's just think of a waterbed, and you put a bowling ball on it. The waterbed sinks, doesn't it? Just like here's the waterbed, here's the bowling ball sinking. Any object that passes by will tend to fall towards the actual mass, won't it? So that's kind of how gravity works. And when you have an object like the Earth that's really, really massive, and you have this little speck over here that flies by and shoots past it for just a second, it will exert force as it goes by the entire time. That force will grow, shrink, 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 shrink. But how much force will that actually be? Well, it depends on the object, and it depends on the mass, and it depends on the velocity. So it really boils down to the momentum. It's not going to be very much. The moon orbits around the Earth continuously every single day, and yet the moon does not have too much of a braking effect on the Earth. It has a little, but not too much. Every time the moon is going away from the Earth, heading backwards, sort of, it's braking the Earth a little bit, and yet nothing major happens. What I'm trying to boil this down to is the understanding that a rogue comet meteor is not going to fly past the Earth, most likely, and halt the Earth to such a degree as to cause any type of negative effect to the Earth. It could happen, but it would almost require something the size of our moon or bigger going past the Earth to truly cause a problem. There's evidence that suggests the moon came from the Earth. There's evidence that says it didn't. Either way, all those masses moving around the Earth has never done anything like this. So just take this into account when you worry about such things. It'll be alright. Anyway, this is Tom from anti-tom.com. I'm out of time. Let me know if you have any questions. Bye-bye.